Okay, so I'm going to talk about the statistical physics of deep learning, and actually it's really nice to go after all the previous talks because a lot of the ideas that you've seen, random matrix theory, and so on and so forth, will appear in this, as applications in deep learning. So, I'm actually a theoretical neuroscientist, so I spend a lot of time understanding how real biological circuits work, and I actually talk to experimentalists and design experiments with them, make predictions, to analyze data, and so on. So we've actually been using deep learning to model the retina, the first steps in seeing. We've been trying to understand how flies see. We've been trying to figure out how mice navigate, how monkeys reach, how learning occurs in mutants that have enhanced synaptic plasticity, and so on. But I think there's a lot of room for unifying neuroscience and deep learning through the following kind of line of logic. So here's the line of logic. We'd all like to understand how the brain works to some extent, but the question is, what does it mean to understand how the brain or a neural circuit works? Well, what we would like is we'd like to understand, for example, how the connectivity and dynamics of a neural circuit gives rise to behavior or cognition. And we'd also like to understand how neural activity and synaptic learning rules conspire to self-organize useful connectivity that subserves learning. Okay, so we don't have all of the data to answer these questions in neuroscience yet, but we actually already have all of this data in machine learning. So the field of machine learning has generated many different types of learned neural networks that accomplish interesting functions that we know of no other way of doing in any other artificial system. The scary thing is we know everything about them. We know their connectivity, we know their dynamics, we know their learning rule, we know their entire developmental experience through their exposure to training stimuli, yet we don't have a meaningful understanding of how they learn and work. Nor do we even have a benchmark for what such understanding would even look like. That's quite scary, actually. So it's an interesting warm-up problem for analyzing the brain or trying to understand the brain. And we kind of wrote out an argument for this in this current opinion piece. So we've been thinking about that, and I'll tell you several stories. These are all published, so you can find the reference. I'll give you the references on the next slide. My purpose here is to try to give you an overview of many different stories, but give you the intuition behind the stories. So the first part will be actually a shallow result, finding optimal algorithms for nonlinear regression in high-dimensional data analysis. And the theme will actually be to always go from ideas in physics to better machine learning algorithms. Each field has its own culture, and the field of machine learning has a culture of, if you can't give me a better algorithm, I don't want to listen to you, okay? That's a bit of annoying for physicists who really want to understand what's going on, but that's how you can connect to them. So if you have a good idea, it should be able to translate into a better algorithm. That's the benchmark for progress in that field. I'm not always sure that it's the right benchmark, but that is the way the culture is at the moment. So a lot of these works, we used ideas from physics to come up with interesting or better algorithms. Okay, so here we found optimal algorithms for doing nonlinear regression in high-dimensional data analysis. That's the first story I'll tell you. The next one is about what is this business of local minima? Why might we not get stuck in local minima? And so there we can exploit ideas from the statistical physics of high-dimensional landscapes to train neural networks. Then I'll talk about modeling complex data distributions by using ideas from non-equilibrium thermodynamics. Then I'll show you that deep neural networks have chaos theory actually as a subset of whatever of their theory. We'll try to understand, what deep functions can express that shallow functions cannot, using the theory of chaos actually. Then we're actually going to use ideas from random matrix theory, especially free probability theory, which governs the spectra of products of random matrices, to essentially speed up neural network training. And the last part, we probably won't get to this, but this is not a deep learning thing, but a general physical analysis of fundamental limits of energy and speed in physical communication. So these are all the references. So we've actually been spending a lot of time. None of these works are actually in neuroscience or involve any experimentalists. These are just pure theory or simulation work on deep learning that we've been doing over the last 3 or so years. All of these publications you can find on our website. I can't possibly talk about all of them, but the blue ones are the ones that I'll touch upon in this talk. But in case you don't get any details, just know that there are references that you can go to get all the details. Okay, so let's start with the first topic, optimal algorithms and nonlinear regression in high-dimensional data analysis. So what is high-dimensional statistics? It's actually kind of a relatively new subfield of statistics that deals with the modern way that we now collect data, right? There's been a cultural revolution in the way that we collect data. We collect many, many large data sets with many numbers of variables simultaneously without knowing in advance whether those variables are useful or not. So to understand high-dimensional statistics or modern statistics, it's useful to compare it to classical statistics, right? Before, when we did an experiment, we knew ahead of time exactly what we wanted to measure, right? So for example, if you want to understand how a neuron works, you know ahead of time that you need to measure the membrane voltage and current across the cell membrane. So there's sort of two variables that you measure, and you measure those two variables in as many conditions as possible. So this is a scenario where the number or the dimensionality of your data is order 1. The amount of data is quite large. So the measurement density, well, there's one over that, but in any case, so you basically have lots and lots of data in a low-dimensional space. Here, what's going on is, for example, in the brain, we can record hundreds to thousands of neurons at once, but not in that many experimental conditions. So the dimensionality of your data is becoming large, the number of data points is becoming large, but the ratio is order 1, okay? The closest thing you can imagine is sort of 3 points in a three-dimensional space, and the question is, how could you discover patterns in such data sets without hallucinating the existence of such patterns? For example, these 3 points form a triangle. Should we be surprised by that or not? Obviously, we should not be. But there are other hallucinations of structure in high-dimensional data that are not as obvious that go on. So we've been working a lot on this high-dimensional statistics. And for physicists, if you're interested, we wrote a long review on the statistical mechanics of complex neural systems and high-dimensional data. I think for this crowd, after the intro talks that you've seen, this might be a great way for non-physicists to learn about the replica method, and also for people who know a little bit about the replica method and cavity method to see how it applies to a variety of topics. So in a unified way, we discussed neural network dynamics, learning dynamics, random matrix theory, random projections, compressed sensing, and so on and so forth. So I think this, feel free to send this to your graduate students or postdocs. I think this might help in sort of getting an entryway into this subject. Okay, so what is the problem of optimal inference in high dimension? So Professor Kabashima talked a little bit about this in compressed sensing. This is kind of a generalization of compressed sensing, where let's say that you have some unknown vector, S0, that you'd like to estimate. You don't get to see S0 directly. You get to take measurements of it, and each of those measurements is a dot product of S0 with some measurement vector, x mu. But that measurement is noisy, so it's corrupted by some additive noise, okay? And so then you get a measurement y mu, okay? So you get access to the inputs and outputs. So you can think of x mu as an input, y mu as an output. This is your training data. And from this training data, you have to estimate an S hat, which should be close to S0, right? So let's say you have a p-dimensional signal, so S0 is p-dimensional. The components are drawn IID from some distribution. It doesn't have to be Gaussian. It could be in some arbitrary distribution. And you get to take n measurements, okay? And the noise is, again, IID across your measurements, but it comes from some noise distribution. A critical parameter is, of course, your measurement density. What is the ratio of the number of measurements to the number of unknowns that you'd like to estimate? Okay, so that's this is the generative model for your data. And now the question is, how do you go from your data to an estimate S hat? Well, a very classical method of doing this in statistics is called an M estimator. You say that S hat is the minimum over all possible candidate signals S0 that you're trying to estimate. You penalize deviations in measurement space, so x mu dot S would be the noise-free measurement that you would get if S were the signal. Y mu is the measurement that you got. So you want to penalize the deviation. So you have a loss function rho that penalizes this deviation. It's monotonically increasing in its argument. And then you may try to regularize the problem by regularizing or penalizing, say, large deviations in Sj, okay? So the estimation algorithm in the data is the specification of a loss function, a regularizer. And for performance, we're just going to use Q sub S, which I'll call the L2, which is the L2 estimation error. It's just the average per component estimation error. So this is going to be a function of the measurement density, the loss function, the regularizer, the noise distribution, and the signal distribution. And so the critical question we'd like to ask is, for a given signal distribution, noise distribution, measurement density, what is the best loss function and regularizer? Okay. So almost every, I skipped a slide. Okay. So There's actually a lot of algorithms can be written in this form. Okay, so for example, maximum likelihood estimation, rho would be the minus log probability of the noise put in here, and sigma would be 0. Map estimation would be rho is the minus log probability of the noise, and sigma is the minus log probability of the signal. You could also use just ridge regression, where sigma is a quadratic function and rho is a quadratic function. You could use lasso, where this is a quadratic function, and this is the L1, or the absolute value function that Professor Kabashima talked about earlier. So that would be the lasso algorithm. So a huge number of algorithms are all special cases of this general form, but now you have an embarrassment of riches, right? Of all the possible algorithms you could use, which one is the best one? That's what we want to answer. Okay, so this is an optimization problem. We can frame it as a statistical mechanics problem, where we just put e to the minus beta of this thing, and that's our Boltzmann distribution, and we take beta to infinity, so we take the zero temperature limit. We use the replica method to compute q sub s as a function of these parameters, and then we actually fix this and optimize q sub s over rho and sigma to find the best rho and sigma. So conceptually, it's a straightforward calculation, but technically it's about 20, 30 pages of calculation, but which you can find in our paper. Okay, so what's the answer? Okay, the answer turns out to be surprisingly intuitive. Okay, let's look at the special case where the signal, for example, is a Laplacian signal. Sorry, the noise is a Laplacian noise, so it has this distribution. The signal is Laplacian, so it has this distribution. Sorry. Okay. So, okay, so this is the optimal algorithm, and it depends on the measurement density. It turns out when the measurement density is quite large, map estimation is the best thing to do, maximum a posteriori inference. So then, the optimal loss function is the minus log probability of the noise. So in both cases, and the optimal regularizer is the minus log probability of the signal. So you want to use the absolute value function for both your loss and your regularizer. Okay? But as you decrease the measurement density, it turns out that the optimal thing to do is a particular nonlinear smoothing of the loss and the regularizer, such that when you get to very, very small measurement densities, the nonlinear smoothing yields a quadratic function independent of the signal and noise distribution, as long as the signal and noise distribution are log concave. Yeah? Uh-huh. In the sense of the smallest mean squared error in the estimation. This also yields the best generalization error for this problem as well. No, I'm not assuming that. So the algorithm never has access to S0, but I can score an algorithm by having knowledge of S0. I could score it with an L1. Yeah, I'm not doing that. I'm scoring with an L2 loss. And so everything, of course, depends on that choice. Yeah. There's no structure in the original signal. It's IID across components. Exactly. Although it's interesting, some of the stuff that Professor Kabashima talked about structured sparsity could potentially be incorporated here. Okay. So what's interesting here is that for a small measurement density, the optimal thing to do is actually quadratic loss. Again, independent of the signal and noise distributions, as long as the signal and noise are log concave, which is a technical assumption that we need for replica symmetry not to break. Okay. So here we have a one-parameter family of optimal algorithms that depends on the measurement density. And what's really nice is that this is ridge regression. Ridge regression is really easy to do. So basically what it's saying is when you don't have that much data, don't try really hard to model the signal and the noise. Just use a quadratic loss and quadratic regularizer and you'll do best. And fortunately, that's a very easy optimization problem to solve because it has a closed form solution in terms of linear algebra. Oh, definitely, yeah. So the intuition is basically, I mean, I can't give you an intuition for exactly why the quadratic thing comes about, But what it's saying is if you have lots and lots of measurements and you want to really pay attention to them and use the detailed structure of the signal and the noise. But if you don't have that many measurements, it doesn't pay that much to use the detailed structure of the signal and the noise. You can just get away with a quadratic Gaussian regularizer. That's sort of the best intuition I can give you at the moment. So again, we're not assuming some adversarial scenario. We're sort of assuming that we have the correct model of the data. The data is drawn from the distribution we think it's drawn from. And we're just saying, if I know the distribution, what's the best Gaussian regularizer? And this is the answer. Yeah. I'm not sure. I think this phenomenon of what's the independence of the optimal algorithm from the detailed distribution of signal and noise may be robust. But of course, the detailed structure of what is optimal may depend on your notion of what is optimal, which is a reasonable thing to believe. Okay, the other thing that we could show is that no inference algorithm whatsoever can outperform our optimal algorithm. So we know actually what the best possible algorithm is. It's the posterior mean. So under L2 loss, the best inference algorithm is compute the posterior distribution of the signal given the data and compute the mean. The problem is that's in general intractable because you have to perform a high-dimensional integral over the unknown signal or over the unknown signal space. So, but it turns out that if you solve this optimal optimization problem, the answer that you'll get will be the same as the posterior mean. Okay, and we sort of showed that in this paper. And this is the paper we worked out the rest of the stuff I've told you. So here's an example. So this is the measurement density. This is the Laplacian signal and noise. The solid curves are theoretical predictions from replica theory. The error bars are numerical simulations. This is the normalized L2 error, normalized by the energy in the signal per component. So this is literally the fraction of unexplained variance in the signal. And so as you can see, at large measurement density, map estimation does best. The red one does best. At small measurement density, quadratic or ridge regression does best. The blue one does best. And the optimal one is, of course, always the best everywhere. Okay? And the quadratic one approaches optimality here, and map will approach optimality here. Okay? So this is an example where you can use ideas from statistical physics to come up with a better algorithm or figure out what's the right thing to optimize, of course, condition on all the assumptions that I made. Yeah. Yeah, there's a particular, the details are in this paper, but what you have to do is you have to compute a Moreau envelope of the map estimator. So with some convolutions and stuff involved. So there's a particular algorithmic process to go from the map estimator to the optimal estimator at finite measurement density. And what I've shown you is examples of this. What it basically does is it does some smoothing, non-local smoothing of this thing. So at some finite measurement density, it smooths out the bottom. And then once you keep on smoothing, you get to a quadratic at the end of the day. The details are in the paper. Okay, so that was shallow stuff. Let's get to deep stuff. So the next thing is a question that came up in the intro talk. When we train neural networks, why don't they get stuck in local minima? I'll give you a story of why they might not. Of course, it's by no means a proof. This is still an open question, but I'll try to give you some intuition for why it's not. Yeah? Yeah. Yeah, the way we phrased it in the paper was there's a fortuitous intersection between computational efficiency and statistical efficiency. It's really nice. So here, statistical and computational efficiency are not at odds with each other. Yeah, I totally agree. That's very interesting. And we noted that. We were surprised by that. Yeah. I should say that there's related work that did, usually that's right here, I don't know why that's not here, but there's related work without the regularizer done by people like Andrea Montanari and also Noureddin El-Karoui at Berkeley, where they showed similar results, but again, without the regularizer. And so without the regularizer, you're forced to be at measurement densities bigger than 1. right? Without any prior knowledge, you must have more measurements and unknowns to ever have a hope of getting finite error. But with the regularizer, you can push forward or backward, so to speak, to measurement densities below 1. Yeah. Oh, yeah, that's only because the signal and noise distributions in this particular example happen to be the same. If they're different, these two will be different as well.
I see.
Yeah.
Okay.
Okay, so again, this goes back to the problem of local minima in neural networks. So here's the story, right? So it's often thought that local minima at high error may stand as a major impediment to non-convex optimization. So this is a cartoon picture of a protein folding landscape. And indeed, there are it's a landscape over 2 variables. And indeed, there are lots of local minima at high error. And the global minimum is at far lower error, or in this case, energy, okay? But we know that our intuition about functions derived from living and moving within a low-dimensional world are woefully inadequate for thinking about the geometry of functions in high-dimensional space. It turns out that random non-convex error surfaces over high-dimensional spaces, for those surfaces, local minima at high error turn out to be exponentially rare in the dimensionality of the domain. Okay? Instead, saddle points proliferate. And so we developed an algorithm that rapidly escapes saddle points. And so these are kind of a pair of papers that appeared where we kind of came to similar results, but using different methods. These guys looked at spin glasses. We looked at random Gaussian error landscapes. And these guys made some brutal approximations. We didn't even attempt to make approximations. So, but these 2 papers have a similar story. So here's the idea. So we were inspired by actually, again, work in physics. I think to many of you, this work will be quite well known. For example, Bray and Dean, many other physicists worked on this problem. But Bray and Dean looked at the following problem. They explored just a random generic error surface that had only a smoothness constraint. Okay? So the basic idea is consider a random Gaussian error landscape over n variables. So the basic idea is you have an error landscape, let's say over the synaptic weights of a deep neural network. Okay, and at each point, so this is the component W1 through Wn. At each point, E is a random variable. And if I evaluate E at one point EA and the error at another point B, these will be jointly Gaussian distributed with some correlation that falls off as e to the minus WA minus WB over lambda, right? So, so basically the surface is a random surface that's smooth over some correlation length scale lambda, but otherwise is wiggling around in n-dimensional space. So that's my model for a random error landscape. Okay? So now pick one random error landscape once and for all. That's your notion of quench disorder. Okay? Now let X be a critical point where basically the gradient of the function vanishes. So partial E, partial W vanishes. Okay? You can take every such critical point and plot it in a two-dimensional feature space. One axis of this feature space is the height of the critical point, the error level, or energy level. And the second axis is the fraction of negative eigenvalues of the Hessian. So you can take the matrix of second derivatives, partial E squared, partial squared E, W1, partial W2. That's a matrix, a metric matrix. It has an eigenvalue spectrum, and F is just the fraction of negative eigenvalues. Okay, so you might think that these critical points could a priori appear anywhere in this two-dimensional feature space, but it turns out they don't. They concentrate on a monotonically increasing curve, and deviations of critical points away from this curve are exponentially suppressed in the dimensionality, okay, of the problem. That's a very good question. We don't know. I will give you numerical evidence that this qualitatively holds in deep neural networks in a couple of slides. Yeah. Sorry, say it again.
What is error level? How you can you please explain again?
Oh yeah, so right now, you shouldn't really think of it as error level. I'm using this language because I'm going to apply it to deep neural networks in the future. But we're just thinking about a random scalar function over n-dimensional space. And it's a random Gaussian process over n-dimensional space. I'm just calling this function E, or error. It doesn't have to be positive, yeah. Could be negative, but that doesn't matter. You can always add a constant offset. It's a Gaussian process, yeah. This statement is a statement about Gaussian processes. No, it's not about error. I'm just using the word error because that's what I'm going to apply it to in a future slide. Sorry, did you have a question? Exactly, yeah. You could call E energy, error, excellence, I don't care. All right. Yeah. Yes. It turns out the detailed behavior of this correlation function near the origin matters a lot. You can make it very rough or smooth or whatever. There's a universality classes of correlation functions that have this behavior, and this is one member of that universality class. Yeah. Yeah.
Statement about the critical points of this Gaussian process.
Exactly.
Calculating the Hessian matrices.
Exactly.
And they're plotting the fraction of negative eigenvalues versus.
So basically, yeah, you find a point where partial E, partial W evaluated at a point W star equals 0. At that point, you compute the Hessian, which is partial squared E, partial W I, partial WJ, Hij, evaluated at W star. This is a random matrix, right? If it's a local minimum, then every eigenvalue is positive, and locally that thing's a positive definite quadratic bowl. If there's some positive and negative eigenvalues, that means at that critical point where the slope vanishes, right, it's a saddle point where some directions curve up and some directions curve down, right? It's like the surface of a saddle. Okay, so that's kind of the geometry of every critical point. It's characterized by, of course, slope 0 in order for it to be a critical point. And then this is the quadratic approximation to the geometry in the vicinity of that critical point. That's what we're talking about. And so the fraction f is the fraction of negative curvature directions that we care about. Exactly. Exactly. Exactly, yeah. So I was about to say that. So basically what Bray and Dean found is that these critical points concentrate on a monotonically increasing curve. Okay, the global minimum sits here. It has the lowest error, or value of E. And of course, because it's a global minimum, the fraction of negative eigenvalues is 0, right? The maximum sits here. It has the largest E, and the fraction of negative eigenvalues is 1, okay? But then as you find critical points at higher error, they develop more and more negative curvature directions, okay? This has two major implications. There are no local minima at high error, right? This region, high error and local minimum, is forbidden. Second, if you're a local minimum, your error level is close to that of the global minimum, okay? I.e., if you have a fraction of negative eigenvalues here, your error level better be close to that of the global minimum. Okay, so basically, the basic intuition is, again, as you go, let's say you have a function over a million-dimensional space, right? Say the million weights of a neural network. You find a point where the slope of your function vanishes. What are the chances that every direction goes up? The answer is exponentially small in the dimensionality, unless you're already near the bottom and there's no place to go but up. That's the intuition. Yeah?
How does the shape of this curve qualitatively change as a function of n?
It doesn't. So this is a well-defined limit as n goes to infinity.
Oh, this is...
Yeah. It turns out this is the cumulative density function of the Wigner distribution. So what they were able to do was they're able to show even more than this. Right? One way to think about this from the perspective of random matrix theory is this is a random symmetric matrix. Okay? We know that a generic random symmetric matrix from Professor Wadia's lecture is a Wigner semicircular law. But this isn't a generic random matrix. It occurred at a critical point that's at a certain error level. It turns out the error level just shifts the Wigner distribution such that if you're at the global minimum, the Wigner distribution is shifted like this, so everything's positive. As you go up, the Wigner distribution shifts over. So when you're halfway up, it really is a Wigner distribution. You can't feel the max and the min. So you're a generic random symmetric matrix, so you're a Wigner. And as you get to the top, all the eigenvalues become negative. So literally, the Wigner semicircle shifts as the error level goes up. And so then that curve becomes the cumulative density function of a semicircular law. That is a detail that depends on the fact that you're random Gaussian, I think. Okay, so that depends on this kernel, right? So with this kernel, you do.
One question. Sorry. When you map this onto machine learning setup, the number of data points is very important. There is some sort of trade-off between the number of parameters. If the number of parameters is much larger than the number of data points, then there should be a lot of directions.
There'll be a lot of flat directions. Yeah, exactly.
So I guess the question is, how does it sort of, in your picture, how does it map?
So here there are no flat directions because the kernel is isotropic, right? It's a full rank kernel, so there are no flat directions. We're not really modeling the flat directions. Yeah. So let's so I will show you. There would definitely be, the shape of the error landscape would depend, of course, on the number of examples that are contributing to the error. There's no way around that. But the question is this monotonically increasing structure quite universal? That's the question. Okay? I would guess presumably larger, right? But I think you'd get the same picture, even if it were smaller. It would just be a different shaped curve, and then there'd be a bunch of eigenvalues that are zero. Again, this is the fraction that are negative, right? So it's not sensitive to the zero ones. We did. I'll show you, yeah, in a little. I'm not like numerically computed it. Okay, okay, now at this point, as physicists, we're used to the notion that there are certain questions whose answers don't depend on the details, right? For example, critical exponents only depend on the symmetry and dimensionality of the order parameter and so on and so forth. And so one might expect that this notion of a monotonically increasing curve, if not its exact shape, might be a universal quantity. Again, we're looking at a scalar function over a high-dimensional space, and the intuition that I articulated should hold, right? Just at a generic point between the max and the min, what are the chances that every direction goes up? Exponentially small in the dimensionality, unless you're already near the bottom. Okay? In which case there's nowhere to go but up. That generic idea we hope would be universal. Of course, computer scientists don't believe in universality at all. They always think that what they're doing is extremely special, and that the stuff these physicists are doing with these random problems are completely irrelevant to what we're doing. We're not training our error landscapes are not random. We have CFAR10 and MNIST and ImageNet and all the structured data on a structured architecture. We're never going to see this, okay? So I teamed up with Yoshua Bengio and said, we should try to plot this function for deep neural networks numerically, right? So we did that. He had an army of graduate students kind of look at this problem. So what we did was we used Newton's method to search for critical points of any index. I'll explain Newton's method on the next slide, but let me just tell you right now that Newton's method is a method of traversing a landscape that actually gets attracted to saddle points, okay? And so then we started Newton's method from random weights, right? This is on a three-layer neural network trained on solving MNIST. This is a larger neural network trained on solving CFAR10 for the parameter regimes and data amounts that are relevant to deep learning, right? And these are the critical points that we found. I can make no claim that this is an unbiased method for searching for all critical points. This is just what Newton's method gave us, starting from random initial conditions. And as you can see, they sort of concentrate on a monotonically increasing curve, both for MNIST and CFAR10, right? This is the actual distribution, and you can see there's a delta function at the origin corresponding to the flat directions that Misha, you were talking about. And so it's qualitatively consistent with the statistical physics theory of random error landscapes. Okay. So, okay, again, what is Newton's method? So Newton's method is you take a step down the gradient, right? But you pre-multiply by the inverse Hessian, okay? The reason for doing Newton's method is it descends a quadratic bowl in one step, right? So if you use Newton's method and you're minimizing a function that's really a quadratic, no matter where you start from, you'll get to the minimum in one step, okay? That's the theoretical reason for this update, okay? But as you can see, it's going to get attracted to saddle points because along a direction of positive curvature, the eigenvalue associated with the Hessian is positive, so that's great. You're going in the negative gradient direction, so you're going down. But along a direction of negative curvature, you have an extra minus sign coming from the negative eigenvalue of the Hessian, okay? But then that negative eigenvalue turns you around and you go uphill. So along this direction you go uphill, along this direction you go downhill, and in general you're attracted to saddle points, okay? So what was an algorithm that was motivated theoretically by descending a quadratic bowl in one step turns out to be a horrible algorithm for non-convex optimization, unless, of course, you modify it in some way. And there's various ways to modify it. The way that we chose was to divide by the absolute value of the Hessian, which is by definition a matrix that has the same eigenvectors of the Hessian, but all the eigenvalues are replaced to be their absolute value. So that gets rid of the sign problem. And there's actually a way to derive this algorithm using a truss region method, which I won't get into. Okay? So we call this a saddle-free Newton's method. It's motivated by, it gets rapidly expelled from saddle points. Okay, how does this do? Yeah?
So your alpha goes up to 0.25 here, right?
Yeah.
Would you have gotten the rest of the curve if you followed Newton's method without the negative sign?
Oh, sorry, this was with Newton's method.
Yeah, but you only got alpha up to point.
Yeah, I suspect that's because of the delta function at the origin. There's so many flat directions that a lot of them get sucked into zero for this problem.
Okay, can you go to the next slide?
Yeah.
So now if you had delta x equals without the minus, right? If you just moved in the direction of the gradient.
Without the Hessian?
Without the minus, without the negative. So with the absolute value, but without the negative.
Oh, I see, okay.
So would you then get the rest of the curve?
No, that would still be repulsed from critical points. You just go uphill away from the critical point. Yeah. Yeah, this is the only one that gets attracted. I mean, of the two algorithms on here, this is the only one that gets attracted to saddle points. Okay, so how does this algorithm do? So what we did was this is for a deep autoencoder model, and this is a recurrent neural network model. You can find the details of the training data and all that in the paper. But we started from just stochastic gradient descent. So just roughly you can think of it as gradient descent, okay? And so that's this blue curve, and then it kind of gets stuck. You see a plateau for both problems, okay? So normally when you see a plateau like this, you might think, oh, I've gotten trapped in a local minimum, okay? Oh, sorry. The y-axis is the error, and the horizontal axis is the number of gradient steps that you take. So you start with random weights, and then you take gradient steps, and so this is how the error falls off as a function of learning time. Right? All the grad students at Google and Facebook stare at these curves all the time, and they optimize hyperparameters to try to get them to go lower, and they make lots of money. All right. Okay. So this is a learning curve of the neural network, and so you see this plateau. So when you see a plateau, you might think, oh, maybe I'm trapped in a local minimum. Okay, but actually, if you switch then from gradient descent to saddle-free Newton, suddenly the error goes down again, okay? So actually that wasn't a local minimum, it was a saddle point, and there was some shallow negative curvature directions that gradient descent had a hard time exploiting. But saddle-free Newton, because you're dividing, a shallow direction corresponds to an eigenvalue that's close to zero. So when you divide by something close to zero, it's large, so you rapidly escape it. So, oops, I was not supposed to do that. Okay, good, all right. So I thought I shut everything off. Okay, so you get this sudden drop. So actually that was a saddle point, and saddle-free Newton, got you down, yeah?
Actually, there's a question. How do you, how can you be sure that it's actually a saddle point and not just something which is not a saddle point but have a very low, incline, very kind of flat region? Because when you're dividing by that, you are taking a gradient step effectively, which is 1 over lambda I, right? So it's huge. So it's like a huge gradient descent step in some sense.
Yeah, it's a good question. I mean, a flat plateau. Yeah, we're not sure, right? It's basically what would happen is, stochastic gradient descent would be slow in either case. So what we should do actually is use Newton's method here and compare Newton's method to saddle-free Newton. That's the test to answer your question. But what we did actually do that's not on this thing is that we monitored the spectrum of eigenvalues of the Hessian, okay? In fact, we monitored the maximum negative eigenvalue. And what happened was whenever it rapidly went down, the negative eigenvalues peaked, right? So there's a separate plot where we plot the negative eigenvalues as a function of training time, and you always see a peak there. But yeah, another good way to do it would be to compare Newton's method to saddle-free Newton's method to discriminate those two possibilities.
Question?
Yeah. There's lots of, so we did this for relatively small problems where there's about 1,000 to 2,000 weights, so we could do it, right? The reason this isn't a full solution to the problem is because computing the Hessian is very difficult, right? If you have 1 million parameters, this is a 1,000,000 by 1,000,000 matrix. And so there are various methods in machine learning for computing the Hessian in low-dimensional subspaces. And so actually an interesting line of future research would be trying to use those approximate Hessian calculations for the absolute value of the Hessian. I mean, that's a major research direction, sort of, that for going forward. Yeah?
So presumably this was not a natural gradient method, right? If you had done natural gradient, would it still have escaped the saddle point?
We have not tried natural gradient on this thing.
Because it also involves some kind of divide.
It involves pre-multiplying by an inverse metric. Yeah. Usually that's not related to, that's related to moving a direct, because there's a mismatch between the metric and parameter space and the natural metric that's relevant to your problem, say fish information and the output probability distribution of the network. And so the natural gradient's sort of solving a different problem, which is solving that mismatch between your parameters and your natural metric. It's kind of, I mean, you could combine the two. I mean, they're orthogonal enough you could combine the two, potentially. Yeah? Oh, so every time saddle-free Newton got a drop, along the trajectory, the number of negative eigenvalues of the Hessian and the magnitude of the most negative eigenvalue went up. Right? So it's as if it's traversing a direction that has many negative curvature directions, or traversing a region of parameter space that has many negative curvature directions. Yeah, definitely. Yeah, symmetric matrices have real eigenvalues that could be positive or negative. Yeah. Yeah, I mean, in fact, a random symmetric matrix has half negative eigenvalues always. Yeah.
So is there a reason why you didn't just consider the subspace of negative eigenvalues of the Hessian and move within that subspace rather than choosing to...
Because the gradient also matters, right?
And project the gradient onto that subspace?
You could, yeah. We didn't. Yeah, we didn't try it. Yeah, it's unclear whether. I mean, the gradient has a projection onto the positive eigenspace as well, right? So it's unclear what's more important: a large magnitude gradient on a positive subspace or large negative curvature. It's unclear which one's more important to follow. So we didn't try messing around with that. Okay, so that's sort of, so again, it's still an open problem, right? We haven't proved anything about the error landscape of deep neural networks. We just exploited ideas from generic Gaussian landscapes, mumbled something about universality, but that actually taught us something that a numerical experiment that we could do in deep neural networks. Okay, but it's still an open problem. Okay, so this is a fun one. It's using, trying to model complex distributions using ideas from non-equilibrium thermodynamics. So here's the basic idea. So there's a whole nother aspect of deep learning that's not just classification. It's actually modeling complex data distributions, right? And so this is sort of the goal of unsupervised learning. We think that if we can just model the world, then we can condition on some aspects of the world and make inferences about other aspects of the world, and thereby reason about what's going on, right? So trying to model a complicated probability distribution is a major industry in deep learning. It's called generative models. Okay. So this is work led by my postdoc, Joshua Soldikstein, who's now a researcher at Google Brain. So this is learning deep general models by reversing the flow of time in a diffusion process. Okay, you'll see its sort of physical origins. So here's the basic idea, right? Let's say we have a complicated data distribution, say the space of natural images in pixel space, right? We don't know how to mathematically write down that distribution, but we'd like to model it. We'd like to sample from it, for example. So the physical idea is the following. This is a complicated distribution, so let's destroy the distribution and make it a simpler distribution, like a Gaussian, through a diffusion process. Okay? Let's then carefully record this destruction of structure. It's like a movie that destroys structure in data. Then we're going to use a deep neural network to reverse time and essentially create structure from noise. Okay? This is inspired both at an intuitive level and at a mathematical level by recent results in now not so recent results in non-equilibrium statistical mechanics, which show that entropy can transiently decrease for short timescales. Think of the Jarzynski inequality and the fluctuation theorems that show that the second law of thermodynamics is, of course, fundamentally statistical, and for small systems, entropy can transiently go down, which means you can create order from noise transiently. These are so-called violations of the second law, but they're not really violations. Okay. So again, just to drive home the point, imagine this die density. Think of it as a complicated probability distribution. We would like to learn the structure of this probability density. And so, of course, if we you think of each point as like a data point in the space, if we let the distribution diffuse, it will become a simpler distribution, ultimately becoming uniform, right? Then if we record this destruction of structure, we can recover the data distribution by sampling from a uniform distribution and feeding it through a deep neural network that's trained to reverse the flow of time. And then we can get back to the data distribution. So basically, we can go from the uniform distribution to the data distribution using a neural network. Okay? There's actually methods for training this neural network that involve minimizing the KL divergence between the forward trajectory and the reverse trajectory. It turns out that KL divergence is a measure of heat dissipation, right? In irreversible systems, the distribution over forward trajectories and reverse trajectories are the same. So there's zero KL divergence, but if you're irreversible, then forward trajectories have higher likelihood than the reverse. So that's irreversible, and that's also directly related to heat dissipation. So we use that as our objective function, it turns out, and we use that to train the neural networks. But actually, let's see if this will work. We'll do increasingly complicated distributions as examples. So this is a kind of a toy model of a complicated distribution. It's called the Swiss roll in machine learning. Okay, and what happens if we let each data point diffuse according to just diffusion in a quadratic well, right? So diffusion in a quadratic well has as its stationary distribution a Gaussian. So if we let that diffusion process unfold, okay, yeah, it's not going to work. So if we let that diffusion process unfold, this is what's going to happen to the data distribution. It becomes a Gaussian, right? But we have that entire movie, so I'm going to take a neural network, feed a Gaussian in, and have it go layer by layer backwards in time, and I demand that if I go from one layer to the next, I reverse the flow of time by one step. And if I go to the next layer, I reverse the flow of time by another step. So I have the training data to do that, and at the end I should get a Swiss roll. So then if it works, I should be able to take a distribution of Gaussian points and then feed it into the neural network and watch it create structure from noise. And that's what the neural network does, it turns out. Okay? So it doesn't learn a perfect distribution. There's some stragglers here. But as you can see, it basically learns a time-dependent vector field that moves you towards a Swiss roll. Okay? All right. If you missed it, this is the movie again. Okay. So now let's move up in complexity. Yeah. No, okay, yeah. Many data points from the Swiss roll. Yeah.
Only one Swiss roll.
Only one Swiss roll, yeah.
I see. So how does it know to unroll into the Swiss roll?
Oh, because...
Well, why a Swiss roll? Why not something else?
Oh, because the movies that were the destruction of structure started from the Swiss roll and became Gaussian, right? So if I reverse the flow of time and start from a Gaussian and try to get to a Swiss roll, if it works, I better get to the Swiss roll. I can't get to anything else. The only issue is, do I get to the Swiss roll? Yeah. The Swiss, exactly, yeah. I could pick another distribution, like another type of Swiss roll, and it would learn that Swiss roll. Yeah, yeah. Yeah.
Because somehow you gave it a lot of points from that.
Exactly, I gave it a lot of
it's
points.
Built into the system somewhere.
It's built into the training data. Exactly. The entire movie is the training data. Exactly. Yeah. Yeah, that's an interesting question. So let's say I allow it to diffuse longer than the mixing time of the diffusion process. Then the neural network has no training signal for the first part, right? But then once you go, okay, so we need to index time, right? So let's say this is the data distribution, and this is the forward process, right? And let's say this is the mixing time, right? Now the neural network is starting from the Gaussian and trying to go back. Each point is a layer that corresponds to one time step in this process. For this point, it has no signal whatsoever, so it can do nothing and it does nothing. It takes a Gaussian and keeps it a Gaussian. But now, the conditional distribution of the past, given the present, has some information about where you came from. So now the neural network kicks in and there's a training signal and it goes to the Swiss roll. So it's actually robust. You don't need to know the mixing time. Yeah. It better be more than the mixing time. Yeah, exactly. Because otherwise you can't start from a Gaussian. Yeah. You're right, yeah. So you need to know, it must be more than the mixing time, but you don't pay any cost in terms of loss of information if it is more than the mixing time, which is something that physicists have a hard time intuiting. But it's because, again, you're keeping information about the entire trajectory, right? Okay, so let's try it on a more complicated data set. For example, something a little bit closer to natural images, right? So this is a toy model of natural images. It's called the dead leaves model. Basically, it's a generative model where you throw down circles of different radii, okay? The distribution of radii is a power law to match power law statistics of natural images. And it has a lot of structure that's in common with the low-level statistical structure of natural images. For example, you have large homogeneous regions and also sharp edges, and you have angular correlations in the edge as a function of position, right? Okay, so then what we do is we generate lots of dead leaves images, and then we allow them to diffuse. So here, diffusion is each pixel just randomly does a random walk from, say, 0 to 255, It does a random walk independent of every other pixel. So that diffusion process will take a dead leaves image and turn it into Gaussian, into just white noise, right? Spatial white noise. And it'll do that to every single one. So you have a whole bunch of dead leaves images. They're all undergoing diffusion and becoming white noise. Then we actually train a convolutional neural network to go from the white noise back to the dead leaves image. And if that works, we have a neural network model of dead leaves where you can start from white noise and feed the white noise image through the different layers of the network and watch it develop an approximation to a dead leaves image. Right? So when you do that, this is what happens. So this is the white noise. And as you can see, it becomes an approximation. So again, it's not perfect, but it does simultaneously get some things that are hard to get simultaneously. So for example, you have these large homogeneous regions plus sharp edges, and you have angular correlations in the sharp edges as a function of distance. Right? Exactly, yeah, it will. It's kind of like a coarsening dynamics, presumably, yeah, presumably. So you can get quantitative about this. So at the time of publication, this was the next best dead leaves model, right? And I'm not sure if this will play. Yeah, it won't play. But you can sort of qualitatively see that ours look a little bit better, but you can also compute the log likelihood of your data. This is a score of how likely are true models, are true dead leaves images under your probabilistic model. And we do better quantitatively as well. Okay. Now what is all this good for? As I said, if you can understand the statistical structure of your world, and let's say you have some missing data, like there's some fact that you don't know, you can condition on all the other facts that you do know and compute the posterior distribution or the facts that you don't know, right? So that's like inference or filling in. You could do that for images, and that's called the in-painting problem. So we also tried this on textures. So these are bark textures. So we learned a neural network model of bark. And we did something where, you know, we replaced the interior of a bark image with noise, and we conditioned or clamped the pixels on the boundary. And then we fed these pixels into the neural network, and we asked the neural network to fill in its best guess as to what's in the interior, conditioned on what's in the boundary, right? So then it turns out, in this reversing the flow of time of diffusion, information from the boundary propagates into the interior and creates a best guess. Okay? So let's see how that happens. So I'm sorry, the movies are not playing from my PowerPoint, but this is what it fills in. Okay? So at least to the human eye, it looks like a relatively convincing fill-in of the bark. And what's interesting is that this fill-in is completely different from the original piece of bark. Okay? So it's actually imagining something new. It's not just memorizing the data set. Okay? And yeah, so you know, in-painting is sort of one application for this. Oh, whoops. Saw it in the whole image is the context, yeah. So what you're essentially asking is, if I make this square bigger, how do I do? Well, in some sense, I made the square infinite, right? By starting from complete white noise. And I got bark that looked reasonable. So my guess is that if you have a very slim context, right, then you'll just get something that looks reasonable, but it will probably be very different from the original bark. And that's actually reasonable, because bark on the boundary does not deterministically determine bark on the interior, even in the real world, right? So it's unreasonable to expect it to recover the exact same image. Oh, for other stuff, yeah. Yeah. Right now, in painting at a semantic level over global is still an unsolved problem. Yeah. there are generative models like these generative models have gotten quite sophisticated, much more sophisticated than the one I'm showing you here. I'm just showing you this because it's very directly connected to physical ideas. They've gotten much more sophisticated now, where they can actually like take people's glasses on and off, or like turn somebody from a man into a woman, or age people, or all this kind of stuff. But there's all sorts of complicated stuff going on in those generative models. Yeah, they're using these variational autoencoders or these generative adversarial models. They are deep nets at the end of the day. Yeah. They work surprisingly well. I mean, it's a major open question what it is that they're doing. For these generative adversarial networks, it's not even obvious that they're learning a generalizable distribution or kind of memorizing the data set. The variational autoencoders are a little bit better because you actually compute a log probability of the data and so on. Okay, but there's some general lessons to be learned from this, even in physics itself, right? So here, in physics, we want to model probability distributions and even sample from distributions, right? Whenever we're sampling from a statistical mechanics model, we're sampling from a probability distribution. So what do we as physicists often do when we sample? Well, we want to learn a complex multimodal distribution with energy barriers separating the different modes, right? Oftentimes what we do is we model such distributions as a stationary distribution of a stochastic process. We write down a stochastic process that obeys detailed balance with respect to the stationary distribution, with respect to the distribution of the model that we're trying to model, right? And if the stochastic process obeys detailed balance with respect to that distribution, then that's an easy way of knowing that the stationary distribution of the process equals the distribution that we want. But then you have this mixing time problem, right? The mixing time can be quite long. It could be exponential in the barrier heights between different modes, okay? So here, the critical generalizable idea is forget that entire framework. Do not model the distribution you want as a stationary distribution of any stochastic process. Instead, demand that we get to that distribution in a finite time transient non-equilibrium process, right? And moreover, we build this, because we're starting from a neural network, starting from a Gaussian, and in a finite time, we're trying to get to the data distribution. And we build this requirement into the learning process to obtain non-equilibrium models of data. So at the end of the day, we have a non-equilibrium distribution as our model of the data distribution, not an equilibrium distribution. And I think there's lots of ways in physics that this could be used. So the details are in this paper, and we actually have another paper more recently where we have some bells and whistles that we can learn these recurrent stochastic nets that also violate detailed balance. You don't have to have symmetric weights in your recurrent neural network. So these are ways of getting stochastic processes that violate detailed balance to control their distribution to model a desired distribution. All right. So, okay. So technically it's been an hour, so I could stop now, or I could probably do, okay, if anyone wants to leave, I won't be offended, but I'm happy to go till 5 so this one is addressing another question that came up oh, sorry, go ahead.
Two things. So you said that we need, when you run it to a diffusion process, we can sort of force it and get it to go. Like, what is the shortest number of steps you could get it?
Yeah, that's a good question. We haven't, there are trade-offs, right? Like, you could reduce the number of steps, but there's hyperparameters. Like, what we do is we train the neural network to learn a mean and a covariance of the next step distribution. And we have hyperparameters where we could try to crank up the variance, right? So you could shorten the number of steps, but increase the variance of each step. But we haven't explored that trade-off very carefully at all.
Okay. And the other thing, I'm just curious. So you mentioned these variational autoencoders and GANs for generating these images, and I've seen them on the internet where they'll take, say, a Van Gogh painting and then do it in a different painter style transfer. Can you tell us how they do it, or just a short?
Yeah. So they have a deterministic function called style, which is basically you feed the image up to a few layers of the neural networks. You've computed some nonlinear functions of the pixels, and then you compute correlation functions of pixels it's a convolutional network, so you can compute spatial correlation functions of the activations of neurons in there, and you fix that. So you've kind of computed some kind of texture or style of the image. Then what you do is you try to find a new image that's close to the, so let's say you have a Picasso of something, right? Then what you do is you try to find an image that's close to the Picasso, or you have a new image that's not a Picasso. You try to find a perturbed version of that new image that has the most similar style to the Picasso. So you try to minimize the discrepancy between the style of the new image and the style of the Picasso. That's a very rough description of what they're doing. But it's actually quite cool that certain correlation functions in the deep layers of a deep network intuitively correspond to the human perception of style. That's what's surprising. Right. And once you have that, there's various ways to do the transfer. Okay, so here we're actually going to use ideas from dynamic mean field theory and chaos theory to understand the expressivity of deep networks. So this was a question that came up, which is what can a deep network compute that a shallow network cannot? Okay, like why is depth good? This is one possible answer, so this is work that was done with my grad student Ben Poole and postdoc Shubhani Lahiri, and also a collaboration with Maitha Raghu and Joshua Soldikstein at Google. So here's the basic notion of expressivity as thought of by computer scientists, right? So the basic question is networks with one hidden layer turn out to be universal function approximators. So if you have the input, you have a hidden layer and the output, you can learn any function whatsoever over input space. Okay? So why do we need depth? Well, these universal function approximations are a little bit hokey because it doesn't tell you how many units you need to have in a hidden layer. For some functions, you may need to have an exponential number of hidden units in the hidden layer, or exponential in the number of input units, right? So just because networks of one hidden layer can universally approximate any function, it doesn't mean they can do it efficiently with a small number of units. Okay. So the way computer scientists kind of think about this is the overall idea is that there might exist certain special functions that can be computed efficiently using a deep neural network, where by efficient I mean a polynomial number of neurons in the input dimension, but cannot be computed efficiently by a shallow network, i.e. requires an exponential number of neurons in the input dimension. Okay? And this idea has intellectual traditions in Boolean circuit theory. For example, when you're constructing Boolean circuits, there's a notion of logical depth as to how many Boolean elements, say AND gates, OR gates, that you have to compose to compute the function. And the parity function is such a function for Boolean circuits. If you allow a decent logical depth, you can do it efficiently, but not if you don't. Okay. People have mimicked this for other function classes. So for example, for ReLU networks, ReLU networks are networks where the nonlinearity is a piecewise linear function that looks like this. So each neuron linearly summates its inputs, a weighted summation, and then passes it through this nonlinearity. Okay, so if you cascade a bunch of ReLU units, then ultimately the composite function that you're learning, let's say you just have one neuron in the output layer, you're learning a scalar function over input space that is piecewise linear. Okay? So one measure of functional complexity might be the number of linear regions. Okay? And so what Montefar and company showed was that you can write down a particular function that has a number of linear regions that's exponential in the depth, right? And that can be mimicked by a deep linear network without using an exponential number of neurons, okay? For some product networks where basically a neuron takes a sum of its inputs and then you have another layer that takes products of inputs and then sums and products, the composite function is a polynomial, And a natural measure of complexity then for that class of functions is the number of monomials in the polynomial. You can again show that you can write down specific polynomials that can be efficiently represented by a deep network, but not a shallow network. And for algebraic topology, there's another, using algebraic topology, there's another kind of thing. Okay, so all of these ideas suffer from the following thing. There's no notion that any of these measures of complexity are natural. There's no notion that the particular function that they wrote down that's efficiently computable by a deep but not a shallow network is natural in any sense. In fact, they're actually quite unnatural. And so they may not look like the functions that we want to compute. And all of this mathematics is very rigid because they look at a particular nonlinearity. They're forced to use a particular type of mathematics. Okay? So one would like a little bit more of a general theory. Yeah, Misha?
You can say that there is another shortcoming of this type of analysis, that there is no notion of learning here. They may be expressible, but they may be very difficult to learn.
Yes, that's absolutely true, yeah. Yeah, we're not addressing the issue of learning in this part of the talk at all. We're just asking, what can a deep network express that a shallow network cannot? Yeah. Okay, so one might think that there's a more general theory out there, and so we're providing a slightly more general theory, where we're combining Riemannian geometry with dynamic mean field theory that allows us to look at arbitrary nonlinearities. We're not forced to, this type of mathematics, which in deep learning is slightly novel, allows us to look at arbitrary nonlinearities, and we look at the curvature of the function as a measure of its complexity. And what we can show then is we can show that even a generic random deep neural network measures of functional curvature grows exponentially with depth but not width. Okay? And moreover, the origins of this exponential growth can be traced to the theory of chaos. Okay? So here's the basic idea. Again, people have always focused on a specific function that was efficiently representable by a deep network but not a shallow network. We're taking a different perspective where we show that any randomly chosen deep network can do something that no shallow network can do with the same number of neurons. Okay? So this motivates the analysis of random deep neural networks. There's another motivation for the analysis of random deep neural networks, which is when you start training, you have to initialize the neural network with some weights. Oftentimes you choose the weights randomly, and it turns out there's very good ensembles to choose those random weights from. That's actually the next part of the talk, which we won't get to. But in any case, this is a prerequisite for that part of the talk, is how do signals propagate through a random deep neural network, which you can think of as a network that's actually used in practice at initialization. Right? So the ensemble is that the weight matrices are chosen IID across layers. The weight matrices, the matrix elements are random Gaussian, but they're not symmetric. They're random Gaussian elements, IID, with a variance sigma squared W over the number of neurons in the previous layer. And the biases are also of this form. The 1 over n is so that the inputs from the previous layer and the bias in the current layer are operating on an equal footing and have order 1 variances. And so this is the dynamics. There's linear propagation to the inputs to the next layer, and then you go through a pointwise nonlinearity to get the activations of the next layer. Okay? So this is a random dynamical system. We can compute the properties of signal propagation through the system. Okay, good. Okay. So the questions that we'd like to ask are, how do simple input manifolds propagate through the layers? For example, a single point. Let's say we put in a single point in the first layer. This is a point, let's say there's n0 neurons in the first layer, or n1 neurons in the first layer. So a single point is a pattern across the n1 neurons, or a point in Rn1. Okay. Does its length grow or shrink as it propagates through, and how fast? Okay. Then let's put a pair of points, so 2 different inputs to the first layer. Do they come closer together or do they diverge, and how fast? And a smooth manifold, let's say we have a manifold, say an image manifold or something, propagating through the system. How does its curvature and volume change? Okay? So these are the questions we'd like to ask. What I'm going to show you is that for random neural networks, the curvature and volume of a smooth manifold can grow exponentially, but it cannot for a shallow network. That's where we're headed. Okay? Okay, so basically, the exponentially in the width. Yeah. So it grows exponentially in the depth, but not in the width of a shallow network. No matter what shallow network. I'll get.
Check.
I'll get to that theorem soon. I'll state the theorem precisely soon. Yeah. Right now we're just looking at depth for now. So, this is a basic question in dynamic mean field theory. For those who know it, you know it. For those who don't, these slides won't necessarily help you, but the paper will. But basically, you can write down. So this is the length, the normalized length of an input vector as it propagates through the layers. You can write down an analytical recursion relation for the length. Okay. This is the theory, so this is the evolution of the length for different values of the standard deviation of the weights. By the way, this is the nonlinearity in this particular example is a tan H nonlinearity or a sigmoid. Okay, and as you can see, there's a nice match between theory and experiment. Okay, what's more interesting is actually a pair of points, right? So let's say you have 2 points, A and B, right? You can look at the matrix of inner products between the pairs of points, a 2 by 2 matrix, and in particular, you can look at the correlation coefficient between the 2 points, okay? And so, or the cosine of the angle between the 2 points, and you can write down a recursion relation for the cosine of this angle, for this correlation coefficient. And what happens is, depending on the standard deviation of the weights, the correlation coefficient can be driven up as a function of depth or driven down, okay? And of course, depending on the standard deviation of the weights and the biases, okay? So, so the solid curves are the theory, the dots are numerical simulations, and they match up nicely, okay? You can write down something that's the analog of a Lyapunov exponent, which is sort of a local multiplicative stretch factor for propagation through the system. If chi1 is bigger than 1, the nearby points are driven apart. And if chi1 is less than 1, the nearby points are driven closer together. Okay? Then you can write down the phase diagram for this network. Okay? There's a boundary in the phase diagram formed by the standard deviation of the biases and the standard deviation of the weights, where here, chi1 is less than 1, and here, chi1 is bigger than 1. Okay? And so basically what's happening is, this is kind of the ordered phase where everything comes closer together, and this turns out to be a chaotic phase where nearby points get driven apart. Okay? Intuitively, what's going on is the following. Because this is a sigmoidal network, right? What's happening is if you have large weights, then the linear weights expand and of course rotate space, but predominantly they expand space. And then the nonlinearity folds space. Then you get expansion and folding, expansion and folding. The expansion's happening in different directions and different layers. So this alternating expansion and folding in different directions is sort of a hallmark of chaos. Right? On the other hand, and of course the biases are independent of the input. So the biases are always trying to point you in the same direction. So the biases are an aligning force. The weights are a decorrelating force. So if the bias is stronger, the weights have to be correspondingly stronger to move you into the chaotic regime. Okay, so that's the basic physical intuition behind this phase diagram. Okay, now what about a manifold as it propagates through the system? Okay, intuitively you expect that the manifold will become very rough in the chaotic regime and still remain smooth in the ordered regime, right? So we can compute, so this is an example of a principal components visualization of the manifold as it propagates through the system, okay? This visualization makes it, so this is at large weights, this is at small weights, and it is smooth here, and it seems to become rough here. We can compute the autocorrelation and all that, and there's a nice match between theory and experiment. This is a nonlinear embedding analysis, something called TSNE. It's a nonlinear dimensionality reduction technique that tries to preserve distances in the high-dimensional space in a low-dimensional space, although it doesn't quite preserve them. And this is what you see in the chaotic regime as the manifold propagates through the network. what seems like what's happening is that the radius of curvature is getting tighter and tighter, and of course it's getting wigglier and wigglier, right? That's a qualitative picture. It turns out that that's completely false, okay? It turns out in the full n-dimensional space, what's going on is the radius of curvature is stabilizing to a constant value, but the curve's length is exponentially growing. So the number of wiggles is growing exponentially, but the radius is order 1, okay? So the curve is wiggling around quite a lot. That's actually what's going on. How do we know that? Well, we can actually analytically compute all of this stuff, right? So if you have a curve, right? If you have a curve embedded in n-dimensional space, there's an ambient Euclidean metric. So you can compute the length of the curve by pulling back the metric. And so this is the metric, and the length is, the square root of this metric. So if you move along a distance theta to d theta along the manifold, the distance you move in Euclidean space is given by this distance. Okay, there's also a notion of curvature, extrinsic curvature for a one-dimensional manifold. So imagine that you have a one-dimensional manifold, right? At any given point, there's a tangent vector and an acceleration vector. That gives you a two-dimensional subspace of the full n-dimensional space. Within that two-dimensional subspace, there's a unique circle called the osculating circle that has the same tangent vector and acceleration vector. That circle has a given radius, and that radius is by definition the radius of curvature of the curve at that point. And the extrinsic curvature is 1 over the radius of curvature. So that tightly curving curves have a small radius of curvature. Or high curvature means small radius of curvature. Okay, there's a formula for this radius of curvature in terms of the velocity acceleration. And so what we can do is, again, we can come up with a dynamic mean field theory for geometry itself and write down a recursion relation. There's also a notion of Grassmannian length, which I won't worry about now. We can write down a recursion relation for what happens as it propagates through the system. But to understand that recursion relation, let's just understand what linear expansion does. So I'm almost done. I'll be done in 2 minutes. So let's understand what linear expansion does to a circle, right? So this is a circle embedded in a random two-dimensional subspace spanned by u0 and u1, two orthogonal vectors, okay? So the radius of the circle is given by this quantity. Let's say I just expand it, then what happens? So here's the expansion. The length of the circle will increase because I expanded it. But the radius will also increase, which means the curvature decreases, right? And then the Grassmannian length, which is roughly the number of times the tangent vector moves around the Grassmannian, or the number of wiggles, stays order 1, okay? So linear expansion expands length but sacrifices curvature, okay? Propagation through a nonlinear neural network does something very, very different. So we can write down the recursion relations. This is the recursion relation for extrinsic curvature. And it turns out to be a leaky integrator, okay, especially when you're in the chaotic regime where the local multiplicative expansion factor is bigger than 1. So whatever curvature there was in the previous layer, it gets attenuated by the linear expansion. But new curvature is added in due to the second derivative of the nonlinearity. So that's the folding. So you get expansion, folding, and this is a leaky integrator, so it stabilizes to an order 1 value, which means that tightening radius of curvature in the low-dimensional plots was an illusion of trying to fit a fundamentally high-dimensional object into a low-dimensional space. So actually, the radius of curvature will stabilize to something that's order 1 that depends on chi2 and chi1, the average second and first derivatives experienced by the nonlinearity as signals propagate through the system. Okay, great. And so what happens is you get expansion, but you get attenuation in addition, and the number of wiggles, which is roughly the Grassmannian length, grows exponentially. So that's actually what's going on. Here's a match between theory and simulation for our recursion relations for curvature. Okay, now here's a theorem, Partha, that you were asking about, is what happens in a shallow network. So in a shallow network where you just go through one layer, here we prove a deterministic result, which is no matter how I choose the weights of this network, I can never get the length to grow exponentially with the width, okay? So now we get to the final result that a random deep neural network, by exploiting dynamic chaos, can get these exponential number of wiggles in the depth. But here, the length grows only as a square root of the width, okay? So there's a depth separation between these systems. Okay, so there's also something about boundary surfaces and so on. So let me summarize. And then so there's only this last part where we use products of random matrices to speed up neural network training. But let me just advertise that we actually used random matrix theory to get much better results. So the blue one is accuracy as a function of time. That's our initialization. It's better than all the others. So that then we can write a paper. All right, thanks. And let me just end with the references. Sorry. Yeah, there's the references. Thanks. It doesn't only apply to the 10H. It applies to arbitrary nonlinearities. But roughly, if you have any saturating nonlinearity with some slope at the origin, you get this similar result. For these ReLU networks, you actually get some different stuff, and we can compute that as well. And so basically, if you give me a nonlinearity, the theory will give you an answer. Yeah, Misha?
I would actually sort of invert your message for the last piece of work that you described. In a sense, you're proving that it's very difficult to learn the things, right?
Yeah, okay, it's a good question. So I never said anything about learnability, right? I was only talking about expressivity,
yes.
right? And so what we're showing is that the chaotic regime, you can be highly expressive, okay? But I doubt that you can learn in the chaotic regime. In the ordered regime, you're basically a linear function. You're not doing anything interesting. And you also get vanishing gradients, right? So it's also hard to learn if you're in the, if you initialize in the ordered regime, right? So what's actually really good to do, and this is what we observe empirically, is it's good to initialize at the edge of chaos, okay? And we studied that very carefully in work that this is in this work, Resurrecting the Sigmoid in Dynamic Isometry. But what we found is in this phase diagram, yeah, let's say this is the phase diagram. There's an entire one-dimensional boundary in which it's good to initialize the system. But it turns out as the depth gets bigger and bigger, it's better to initialize closer and closer to this point. And my intuition for that is you want to be close to the boundary so you don't get vanishing or exploding gradients, right? But what then you can do is you can flexibly deploy order or chaos at different points in input space and basically contract or expand space as needed, right? So these trained networks, we've checked the Riemannian geometry of the input-output map for trained networks, and they do kind of what you'd intuitively expect. They contract space at the center of decision volumes, and they expand space near decision boundaries. So what these deep networks are doing is they're trying to flexibly allocate contraction and expansion regions to different points in input space. To help it do that, it's useful to be poised at the boundary of criticality at initialization, so that it can do that. A different. I think that's just words. Yeah, I mean, you could compute the curvature for 2- and 3-dimensional manifolds. Something similar would happen. We haven't done it in detail.
Nice.
Yeah.
And one last question. So you said there's something to do with random networks. So where is the fact that the network is random? Where is it used in the one-dimensional manifold result?
In the derivation of the recursion relations for curvature. And so basically in the dynamic mean field theory, we assume certain things are weakly correlated, and that comes from the IID assumption on the weights.
Thank you.
And it's a good assumption because of the match between theory and simulation, essentially. Thanks.